In this video, we'll show design features of a typical dehumidifier. We'll describe how permanent split capacitor motors work, and we'll go through a real-world diagnosis and fix of a dehumidifier that will not turn on. Well, some of you may recognize this dehumidifier. You recall I did a recent video where I took it all apart and showed you how it worked. Just last week I noticed it's not working in the boat, so I brought it home to try and diagnose it. Let's turn it on. Did you hear that? That was the compressor trying to turn on. The fan's not going at all. Now when the compressor does that humming sound for a few seconds and then turns off, it does that because it's got an automatic shutoff in it. I've tried it again. It's trying to start, but when the current goes on for too long, it turns the current off because the tiny wires inside the windings aren't able to tolerate big current for a long time. And so that's not good for the compressor. What's the diagnosis? Okay, when you hear a motor doing that, it hums for a few seconds and then quits. That's a specific pathway. They call that a locked rotor. And it's a diagnostic algorithm that leads to a few common possibilities to what might cause that. The first possibility is that the rotor indeed is locked. The motor isn't able to mount the torque to get the rotor spooling up. And so could it be, say, a bad bearing or something mechanical inside the motor that's doing that? The second possibility is that it could be either a short to ground or a short to another winding inside the motor. Or the motor could be an open. There could be wiring damage caused by overheating in the motor. And of course, both those two first possibilities are basically landfill territory. You can't fix either of those with a hermetically sealed motor like this. But the third possibility, and a very common possibility, is the capacitor, and that's a cheap fix. So that's what we're going to focus on today. Okay, first step is to get this apart. These are all Phillips head screws. Okay. And we've got screws here as well. There we are. Whoa, 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 stop right there. I want to pause for a minute and talk about these motors. These little PSC motors are a subcategory of the broad category of AC induction motors, and they're everywhere. In fact, they're the most prevalent motors on the planet. You probably own a half a dozen of these things, and so it's worthwhile knowing how they work so that when they mess up in your house, you know how to approach them. The core of an AC induction motor is a squirrel cage, which is an aluminum drum that spins with the rotor. The cool thing about it is there's no wires leading to the squirrel cage. There are no magnets, no commutator, and no brushes to wear out. It's just a hollow drum. It's not even magnetic. So what makes it spin? All of the windings of induction motors are in this stationary outside called the stator. As current goes through those windings, a rotating magnetic field induces a loop of circular current inside the squirrel cage, which sets up its own magnetic field. So the squirrel cage is dragged up to speed by induced magnetic forces. Now, induction motors are simplest when they're used in the industrial setting, and in that situation, they don't need a capacitor. You just hook up the three wires in the right configuration so that the motor spools in the correct direction. Well, the main problem in residential circuits is we don't have three-phase power. We just got single phase, one phase going in and out, and so we need to find some way of enhancing torque and establishing consistent starting in the same direction. The genius solution was to add a second winding called a start winding, wired in parallel to the main winding. Then you add a capacitor in series to that parallel start winding to shift its phase. They call this a permanent split capacitor design because the one capacitor was in the circuit for the entire time the motor was running. Effectively, that single capacitor was performing two tasks by boosting startup torque and then later correcting power factor for more efficient energy consumption. It turns out the ideal capacitance for starting is about threefold greater than it is for running. So manufacturers decided to modify the design we see today by having two capacitors in parallel with some kind of switch to drop the starting cap out after the motor had spooled up. That's important for you because if you've got one of those more modern designs, you'll want to pay attention to the vulnerable switch as a cause for why your motor isn't starting. The two motors we're looking at today are an old favorite called permanent split capacitor motors, or PSC motors. That means that there's a single capacitor in service for each of these motors for both the start and the run phases of service. There are newer, more efficient iterations that find a way to use separate capacitors for both start and run, but that's a topic for another day. Okay, that's enough for the moment. Let's get back to the repair. Now here's the fan, and it's clearly not locked. And of course, because this is hermetically sealed, we can't tell if the rotor is locked on the compressor. The capacitor is going to be under here, so let's take this cover off. So this is the capacitor here. It was clamped in, I unclamped it. And now we're at a very important stage here. Two issues. One is These things can retain a nasty shock, and so you want to try and short them out as best you can before you start putting your fingers on them, because you'll get a nasty shock. The second point is that these terminals go exactly to a certain place, and if you want to really screw things up, you can mess things up here. So take a picture with your phone of exactly which wires go to where. I've already done that, and so it's easy enough just to take these off. All right, this is the top of the capacitor here, and I'm not seeing any abnormality. It's not bulging, it's not rusted. I don't see any abnormal things. Now, these capacitors, these RUM capacitors are interesting. They're actually two capacitors in one. The C right there, that stands for common. F is fan, and then HERM is for the compressor. And basically two capacitors in one. One capacitor is between the common and the fan, that's the fan capacitor, and one between the common and the HERM. And so we're going to test those individually now. All right, let's test this capacitor. Before you do it, you always short out the windings because you can't have any residual charge on it, otherwise your results will be inaccurate. I'll switch it to measuring capacitance. We'll do the fan first. It should be 6 microfarads. I get 1.4 nanofarads, so that's way low, way low. Now let's do the compressor. 1.36 nanofarads. So again, way low. It should be 45 microfarads. So clearly, we've got a bad capacitor. So it doesn't make any sense to spend the time and the money in getting a new capacitor if the motor windings are bad. And so I'm going to check out the motor windings now. We've set it to resistance testing, and this has to be fairly accurate. So I'm going to hit the rel button just to account for the wires. Now I know the brown wire here goes to common on the motor. And I put it in such a way that it's not spreading the contacts. And first we'll do the start winding, the resistance of the start winding. So red to brown is 2.3 ohms. So I'll write that down. And now we'll measure the common winding. It's brown to blue, and I get 1.0 ohms. So if you put the two together, you should get the sum of those two. So that's what, 3.3? Let's see what we got here. 3.3 exactly. It doesn't have to be perfect, but that looks good. Now the last check is to make sure it's not shorted to ground. And I just do that like this, and we're not getting any short to ground. You could do that with all of them, but basically if it's shorted to ground, it'll be likely shorted with all of them. So as far as I can tell, this motor is fine. Let's get a new capacitor. When looking for a replacement capacitor, you need what's called a run capacitor, which is designed to be under continuous duty. Notice that it has a steel housing in contrast with the plastic housings of some dedicated start capacitors. Dedicated start capacitors are only switched on for a few seconds of each cycle, so they don't have to dissipate the heat of continuous current. Now the rating on this one is 270 volts. Now you might wonder whether the 270 is necessary because your incoming voltage is only 120. It is. You can't swap in one rated for less voltage, but can use a bigger one. When you do circuit analysis, you'll be surprised to realize that the phase shift of a series capacitor and inductor can produce huge voltage drops across both the windings and the capacitor, much greater than incoming voltage. Technicians will tell you those huge drops peak after the motor spools up as back EMF slows current flow during the run stage. It's a few days later and I've got this capacitor off of Amazon. I tried to match it up as best I could. This is 45 plus 5, whereas the old one is 45 plus 6. But I don't think that small difference will make any difference. Importantly, it's either 440 or 370 volts AC, and the other one is 370. And I guess that explains why this one is larger. Let's make sure it fits. Okay, I've got it all hooked up. Fortunately, the larger capacitor still will fit into that box, which is a good thing. I'm going to plug it in, and we'll turn it on and see if it works. All right, let's turn it on. Ha! Look at that, the fan is running. And I can feel the compressor going as well. So I think we've got a fix here. Well, the dehumidifier is back in the boat and it seems to be working well today, even on a cold day like today. I hope everyone did like today. I'd love to hear any comments. Thanks for watching.